Since I came in to KAIST from U.S. Last about just over a year, I really did my best to explain the excitation mechanism. And in this class, I spend some time to give you, then you can capture the essence in excitation mechanism for underwater explosion. If you look into detail, it's very simple mechanism. But if you if you are not be careful, it looks very complicated, but it's not. So it has a basic mechanism, and many efforts were there in the past to really see it, what kind of the explosion, what kind of excitation mechanism we have, and how we express mathematically, and how to solve the given problem. But one of the research area we must pursue is like a Cheonan incidence by something like 300 kilogram TNT. The Cheonan naval ship split into two pieces and sunk right away. It didn't wait. Maybe the backside, the rear part, after it split into two pieces, the front part just sunk, it's gone right away. But in the rear part remained less than an hour. But 46 people died because of that, the torpedo explosion. The question arises always, how to make a safer ship against underwater explosion. That's what we should concentrate to do the research and testing. Testing is very important, and of course the modeling and simulation. So before conducted testing in US, the modeling and simulation, M&S, are the must. That's mandatory for not only just a shock problem, any problem. Before you really make hardware, prototype hardware, you must conduct M&S first, then make a hardware. In our situation for the shock, you have to make some provision to protect the ship against underwater explosion. Then we could conduct the testing. So in my lab, we are slowly moving into that sort of the research. And as you are going to do some term project, you have to now, it's about time to think and start. So something like around the mid-October, you should get together with your partner, and around the end of October, then you have to propose, and actual work may take place for a month of November. Okay, so I don't want you to spend 24 hours a day on that, but I really like to pick your brain on some good idea and conceptual work. That's most important. How to protect my ship, for example, against the shock. So think about something. I have some idea that may be kind of a classical idea. I talked to Char Hong yesterday. He's my student. But your idea may be brilliant. Young idea. That's what Christ is always looking for. That's what everybody's looking for. As I said, it's not step by step. Do this first. Do that next. Do that after. Things like that to get to here. But nowadays, I mentioned to you before, jump from here to here. You skip all the middle part. Is it possible? Yes, it is possible. I look at last night the movie, not the movie, drama in KBS 1. And start at 10 o'clock. It's called 도망자. How do you express in English? 도망자. Fleeing man. The main actor there is P. P? Raining man? Rain man? P. You know the P? You don't know the P. Okay. So, I never seen such a thing. He has a desk. Okay? And the whole thing is a monitor. Then he put the hand on it and click there. You see the image there. And monitor is like over there. Then he throw this image toward the monitor. It appears there. I said, wow, that's what an idea. Put it there. Then it goes right on. There is no middle step. From here, throw it, goes up there. So some idea. So that's the way you should do graduate study in KAIST. Get some idea. It doesn't come from textbook, but all the things shown in the textbook will contribute to bring such idea in your brain. Okay? So that's what I'm doing here. Give you the idea. In 2.2, what am I doing here is I'm going to give you a little bit path, what direction I'm going to discuss with you and why. Okay? And you know about the explosive shock in the water. You know. And you know the phenomena, I'm pretty sure. And you know the underwater shock wave, how it propagates. You learn about that. And you know the gas bubble motion, you know about that. All the phenomena comes first before the math. Okay? Not the math first, then phenomena, no. Always phenomena comes first. Physics part comes first, then on that. In 2.2, what I'm going to do here is I'm going to show you roadmap. Okay. And you may stop me anytime to ask any questions. So if I readily know, I'll answer to you right away. If I'm not sure, then I have to think about it, maybe look at some references, then always get you the answer right next to class, okay? So that's the way we're gonna do. So roadmap here is 2.2. I'm going to show you hydrodynamic relations. I'm not the expert in hydrodynamics. I'm doing the shock wave which relate to the acoustics wave to solve the shock problem. In the hydrodynamics relations, I'm going to show you three different things. I'm going to show you the conservation, very important. Conservation laws. Conservation law. You learned this in fluid mechanics or fluid dynamics. What's the conservation law? Louder.
Conservation of mass, conservation of energy,
Okay. One missing. Conservation of mass, momentum, and energy. That's what you learn. To solve the shock problem through like MNS, all the code is based on the conservation law. Okay. Then in hydrodynamics, it's not really replacing or deriving directly the shock wave relations, but by learning all this conservation law, then I can use acoustics approximations to derive the acoustics relations. Can you see this well? Can you see this? So I'm going to derive this using acoustics approximation. I'll show you. I'm just showing you the roadmap using the acoustics approximation that I'm going to derive directly to the wave equation. I'm going to say shock wave equation. Or I could say acoustics wave equation. Because I'm using all the acoustics data equations used for the shock wave calculation. Why? Because right in the vicinity, our assumption for this course is when the explosion occurs, I'm not concerning the survivability of the ocean structures or ships or submarines in the vicinity of the charge at the time of explosion. Or if some ship or submarine are sitting next to the explosion, all Hassan, Yongshin could say is, Lord help me, you have to pray a lot to your God, because you can't stop them. So some distance away, let's say I said at least 10 times of R. What's RI? Radius of initial charge, size, right? You got it? Right? That's the rule of thumb. Rule of thumb. Then, because the detonation speed and shock wave pressure is extremely high in the vicinity of the charge at the time of explosion, but it decays exponentially as the distance goes away. Shock wave pressure just shoot down. Okay, we all see that in chapter 1, chapter 2.1. So all the acoustics relations then we can use to solve the shock problem. So here we're going to show you about this, the wave equation. In the physics, the college physics, or even maybe, no, not high school physics, I'm afraid. At least the college physics, or through the vibration of continuum system, you learn about solving the wave equation. Maybe yes or no. Wave equation. Yeah, I'm pretty sure you know the wave equation, but I'm going to show you how to solve the wave equation, then apply to solve shock problem. That's what I'm going to do. So here, then here, so I'm going to get the solution. Something like solutions, something like P is equal to rho C V or rho C U. That's the solution. Have you seen this before? Have you seen this before as a solution to the wave equation? Have you seen that? Maybe not. You know, I taught such a classes or 40-hour short course in many different people in many different countries in the past. Even shock expert, they don't recognize this important solution. P is equal to rho Cu. Remember this. P is something like the shock wave pressure. I'm giving you just the first, but I'll drive all this with you. And rho is mass density of the fluid. And C is acoustic velocity in water. U is fluid particle velocity. So P is pressure. P is equal to rho Cu. You must remember. This is strictly speaking, this is good for the plane wave. This is wave front. Is in the water media. And the P here is the shock wave pressure for this wave front. And right behind here is a U, fluid particle velocity. Okay? Velocity is a vector quantity, right? So if a shock wave moves to the right, then of course the fluid particle velocity is also moving in the same direction. And this media is rho C. Rho C is media characteristics, very important characteristics. We're going to derive all that. And it's called characteristic impedance. character. Anyway, characteristic. Anyway, so you characteristic impedance, okay? Which is really, rho C is really telling the property of the media. We are dealing with the fluid media, water media. Air media, rho C in air is about 3,000 times smaller. Well, we'll get into all that, okay? So this is what I do, solution, then apply to the naval problem. Then after you got the solution, then apply to real problem. Mathematician stops here. After get the solution, then that's it. That's what the mathematician stops. But engineer, we go another step to apply to the real problem. This is not the only way to get the solution. Start from the hydrodynamic relations, but you can use a different approach, which I'm going to also do. You use the so-called velocity potential approach. Another approach, which is much more elegant, but using the hydrodynamic relations is direct. You can really see it and feel it. Velocity potential approaches introduce the velocity potential, which you used in fluid mechanics. I know it. But that's the vehicle to get to the solution, to get the destination much faster, much easier. But sometimes everything is in the fog. So then as the plane gets out from the cloudy fog, then everything is all clear. So I'm going to show you from here hydrodynamic relations to have a good grip on it. Then next I'm going to show you the velocity potential approach to get down to the destination. Okay? So this is what I'm going to do. So by the time you finish, it's going to be all clear. Okay, so hydrodynamic relations here. So I made some assumption with the shock in mind. Shock wave. When explosion occurs, everything is done, everything is all done, and shock wave is gone as a matter of second. Done. Okay? So at the time of explosion, it generates the shock wave, which compresses the wave front. Is really compresses the waters and move away fast. But for that time, instant time, the water is still calm, very quiet. And if you stand and see the explosions maybe about 20-30 meters away, a yard away, I can clearly see the wave is really quickly moving away. It's just gone. How? Color of the water changes. Why? It compresses the water. Then I can tell it just quickly, just instantly gone. It has some line just moving away. So that was, but everything's calm, then suddenly is moving away. After the shock wave moving away, then what happened? The gas bubble oscillations, right? Then the water particles start to dancing. Then you can see plumes coming up, white plumes. White plume is by collapse of the gas bubble. Okay? Then eventually you will see the black bubble, black plume comes right into the air, which means all that gaseous product, as the gas bubble vent out into the air, then what happened? All the black stuff, gaseous product, comes right out into the air, and you see the huge, the black plume. Did I show you? Maybe not. The DDG-81 shipshock trier? Maybe not. That's about 30 minutes video, kind of the record document, which is the unclassified version, so you could see it. I'll show you. I owe you U571 and also the DDG-81 shipshock trier for 10,000 pound charge. 10,000 pound means about just over 5,000 kilogram charge. It's a big charge, and bang into it. In Korea, they never have done such explosion. They have done some explosion testing for minesweepers or things like that, but not like 5,000 kilogram charge. Let it explode and see the response. And some basic assumptions we made, because shock is so fast, all this assumption is very reasonable. We assumed the fluid is ideal, which means no shear stresses, there is no heat transfers in and out, and there is no discontinuities in pressure, fluid velocity, internal energy. You have to be very careful. I'm just combining the blackboard writing a little bit and also the PowerPoint to save some time to write out. So when you go back to your office, when you look at this, for example, conservation law, I want you to really sit down to drive all the relation by yourself. Drive yourself, not just looking at it. When you close the book, you will forget. Instantly evaporated. I want you to drive yourself to make sure that you capture the essence of it, okay? You have to drive it. And you learned this before, but if I ask you in the exam paper, drive the relation for conservation of mass, I'm not sure whether you could do correctly or not. So the midterm exam around the third week of October is going to be closed book exam. I want to see it. I don't want you to memorize anything, but I want you to keep all the logics, everything. So there's no discontinuities in pressure, fluid velocity. Fluid velocity means fluid particle velocity, and pressure means like a shock pressure, and internal energy. And we are going to derive differential equations for the ideal fluid. I want to derive this with a goal in mind, which is a shock. Okay? conservation of mass, conservation of momentum, and conservation of energy. As a result, I want to derive and show you the one-to-one relation between the pressure and the density. When I say pressure is like a shock pressure and density is really fluid, the mass density relations, one-to-one relations, that's what I can derive all this. This is very important. The approach we are using for modeling and simulation is arbitrarily Lagrangian Eulerian approach to solve the problem, and this conservation law has to be met in that algorithm. So in the back behind the ALE, this is in there. Okay. Conservation of mass. When you hear the conservation of mass, what do you have in mind? You learned that. I'm just recasting that to you. Then we're going to get down to the solution equations of conservation of mass. Then we're going to use it for shock problem. What's a conservation of mass? Chongwan, what's a conservation of mass?
This is not changing.
No change in mass, right? That's what the conservation law means. No change in mass. But that I elaborate right here. Considering a small, the fixed region of the space in the interior of the fluid. This is a fluid media right here. You're considering just one small fixed region, which I'm going to depict the differential volume, dV. dV is a differential volume, very small, the part of the fluid. And here is this is XYZ is really small dot or fixed, small fixed region. That region is dV, differential volume, which has a dx, dy, dg in XYZ coordinate. Okay? Then you can say the conservation of mass is any change in mass of the fluid. Any change in mass of the fluid contained in the volume is equal to the net change. This is one phrase. Any change in mass of the fluid contained in differential volume dV. Any change in the mass of the fluid dV, small fixed region, differential volume, is equal to the net quantity of the fluid which flows through the boundary surface. It has how many different surfaces? There's the surface in X direction, two surfaces in Y and Z directions. When you consider the Q, okay? So when the fluid comes right in to this differential volume dV, when it comes in, it goes out in XYZ directions, okay? Then the net quantity of the fluid which flows through the boundary surface is equal to the change in mass of the fluid contained in the differential volume. Is it clear? Clear? Definition by statement. Then now we're going to cast this into equation. That's about all. So first, any change in mass of the fluid contained in the volume is I call as a delta M. Okay? So that's a delta M. The delta M, any change in mass, fluid mass, is caused by change in mass density, rho. If mass density is fully constant, then no change. That's a zero. So the change in mass, I'm going to call that as M in time t, during the time duration delta t, okay, at time t, resulting from the change in the density at the point xyz point for the differential volume dV can be expressed by this. I want you to really seeping the statements and convert into the notation, equation set. Delta V, delta M is equal to dV is a fixed, that's a dx dy dz, fixed volume, differential volume, times delta rho. This change in mass for the duration of delta t is coming from the change in mass density. If mass density, change in mass density for duration of time function, okay? In next section I'm showing to see the same in different angle. Otherwise, just mathematics, no ties to physics, shock part of the physics. So delta M is equal to delta rho times dV, right? I clearly said the change in mass M in time t, time duration is delta t. During that delta t, there is a change in mass density. So this delta rho, you can think as a function of the t, time. So I can change that into del rho over del t times dt, because it happened during the time d delta t, okay? And dv just carries over as a dx dy dg. So delta M, of course, this is due to the motion of particle. This particle means it's really a fluid particle. Particle in the fluid. Fluid is infinite collection of a particle. Fluid particle. So delta M is equal to del rho over del t times dt dx dy dg, which is a direct translation of first statements. Any change in mass of the fluid contained in the volume, contained in the differential volume, is exactly this, delta M, okay? Then now we're going to look at the net quantity of the fluid which flows through the boundary surface. Then we'll translate that into the equation. Then we're going to just set the delta M is equal to the second parts of the statements. So second part, I'm using this notation all the time without changing it. So I'm going to say let UVW, of course UVW is a function of the spatial location, which is xyz position, and time t. UVW is fluid particle velocity in x, y, and z directions. Remember, UVW is not just the velocity, fluid particle velocity. Acoustic wave velocity, I use what notation? C, right? C or C naught is what I'm using it, right? And UVW is the notation I'm using it for fluid particles. C or C naught I'm using as acoustic wave velocity. Two different velocity quantity, right? Over here, this shock wave will move with a velocity of C or C naught. That's an acoustic wave. Roughly equal to 1500 meter per second. Then right in the behind here, then there is a fluid particle also moving in the same direction. This is a 1500 meter per second. This UVW, U is in X direction, V is in Y direction, and W is in the Z directional fluid particle velocity. I can explain better than this, very detailed explanation. And U, V, W, and C scale, magnitude is totally different. For the ship shock problem, you are dealing this U, V, W is something like, just roughly something like 10 or 15 or 20 feet per second. Think about P is equal to rho CU. You know the rho C for the water. I'll show you the value. Then P, you know roughly for the to solve a ship shock problem, you know roughly the shock wave of pressure around 1000 psi max. If it's more, ship doesn't survive. If ship doesn't survive, what's good for it, right? So scale is different. So U is this P may be 1000 psi, converting to megapascals. Then you can tell what that is. Rho C, you know. If I say air, then you can compute the rho, you know the C. You can roughly compute that, right? And for water, you can compute that. Then you can compute the U. U is equal to P over rho C. This quantity, this rho C in the water, well, you will see that. So you can compute that, the U. U is range in feet per, in terms of the feet, it's like we are dealing with 10 or 20 feet per second type. So you get the feel of it. So as you see here, UVWB velocity of a point moving with the fluid in X, Y, Z direction is clear, right? Notation. Then first I'm going to consider X directional motion, then Y directional motion, then Z directional motion. I'm going to get the result, equation. Can you then summing three equations algebraically? No, because direction is different. So vector sum, you can do that, right? Not the direct algebraic sum, no, but vector sum, you can do that. So here, I'm going to say this is X phase. Over here, this is X phase. The other side is, the other direction is the Y direction, the other is the Z direction. So this is X phase, and the other side is X plus dx phase, because this distance is dx, right? This distance is dx for the differential volume. So I'm going to say let rho u Rho u has a name, which is really mass of flux. So let's look at what that means here. Mass of flux. What that means. Rho, what's the unit of the rho? Kilogram per meter cube. And what's the u? This is rho. Meter per second. So it cancels up. So now, so this is u. So now you have a kilogram per meter square up second. So I can do this. Or you can do kilogram meter square and second. Mass per unit area per unit time. It's called the mass of flux, okay? So rho c is mass of flux is coming at x phase, right? In the volume, differential volume is x phase, then this is x plus dx phase, right? And the mass per unit area per unit time, what direction is it moving? X direction first. Then you will consider afterward y direction. Then you will consider afterward the z direction. Is it clear? Yes. Should be very clear. Then change in the rho c here, because rho c here is exactly explanation over here. Net quantity of the fluid which flows through the boundary surface. So here, net quantity of fluid mass which flows through the boundary. First, x-directional boundary. Rho c, rho u is mass per unit area per unit time. So I'm going to consider one side it comes in, the other side it goes out. So net change, net quantity change is simply rho u at x phase minus rho u at x plus dx phase. That's a change. Net change is this in what time? During dt time. And what area? dy dg. The area perpendicular to the x direction is dy dg. That's a phase on differential volume, right? It should be very clear. Then to cast into this expression del over del x, then I switch this guy. Okay, this guy, put this guy first, this guy second. Then minus sign comes right out. Then minus comes right out. Then then you can change that. This is x-directional variation. So del rho u over del x times dx, directional, x-directional change, times just the carryover over the dy dg. And of course, dx, dy, dg, dx, this part, look at this part, is this part, okay? Then dx comes from there, dy, dg, carryover, dt, carryover. If you look at carefully here, then you will see that dx, dy, dg is a dv. So that's what the differential volume is. Then you got the equation, x-directional equation is right here. Delta m x-directional, net change of the fluid mass in x-direction is this. Then you can do a similar way for y direction, delta my, and you can do delta mz. Then by the conservation of mass definition, delta m has to be equal to delta mx plus delta my plus delta Z, delta mz. Then you just put all these terms, you can do that in there, then cancel out dx, dy, dz, and dt is all same, then drop it, then you will have this relationship. Or to simplify, using the divergence. This is a divergence. Divergence is a gradient dot. This is a gradient notation, then dot rho v. So we're going to start this from 2:30 right here until 4 o'clock. So I elaborate this quite a bit, then no confusion afterward. Because when you learn all the conservation, it just goes away, then we'll use all this for the shock problem. Okay, I'll stop right here.